I have a holomorphic function which is defined on a ball bar, and inside that ball, if I'm taking a rectangle or a triangle, and if gamma, capital gamma, denotes the boundary of that rectangle or the triangle, then what is my claim is that the integral of f over that rectangle is going to be equal to 0. So what we saw in the last class, that our methodology would be that we are going to subdivide our rectangle or our triangle into four equal parts. Okay, so by joining opposite the midpoints of opposite sides. Okay, so this is what we are going to do. And then if I write, means like we understood that the integral is nothing but sum of the integral of integration of f over the subrectangles or subtriangles gamma I, where gamma I is the boundary of Ri. Okay, and since all of them add up to I, so at least one of them must be having absolute value bigger than or equal to mod I divided by 4. Okay, so we are going to continue this process like so let's say like we decided that, let's say, without loss of generality, r1 has the integral in absolute value bigger than or equal to mod I divided by 4. Then I am going to further subdivide that rectangle or triangle into four equal pieces, and we can continue doing so. Means we can keep doing this, and we will get a nested sequence of rectangles or triangles. Okay, so let me write down a few important facts about them. So without loss of generality, I took I equal to 1. So here note that length of gamma 1 is exactly half length of gamma, right? So you can clearly see that the circumference here, whatever is of the rectangle R, is exactly twice the circumference of the rectangle R1. Similarly, in case of the triangles as well. Okay, so once we have that, what we get is that the length is getting divided by 2. And also in metric space there is this concept of diameter. So diameter means the maximum possible distance between 2 points of a set. So that diameter is also getting reduced by half. Okay, so diameter uh, r1 is half times diameter of r. Okay, so this is what is happening. And now if I continue doing like this, then what I am going to get is that, notice, so here this I over, yeah, okay, so let it be mod I divided by 4. So now if we continue like this, so continuing this way, and uh, further subdividing this way by further subdividing R1 into 4 subrectangles slash triangles. What am I going to get? We get a sequence or a nested sequence of nested. So we get a sequence of nested rectangles or rectangles, small triangles, whichever you want to take. So let's say R1 is equal to R. I write it in the superscript R1, and then I have R2, then so on and so forth. I have some Rn somewhere, and I will keep continuing doing this. Okay, and we have the boundaries also along with the rectangles or the triangles. I'm going to get their boundaries, and their boundaries gamma 1, which yeah, gamma 2, and so on and so forth. Okay, gamma n. So that's the notation that I'm going to use. So I have this. So here, what are the properties? So such that diameter of rk plus 1 is half of diameter of rk, and similarly length of gamma k plus 1 is going to be half of length of gamma k. Okay, so this is precisely what we are getting. And moreover, and if I take the integral of f over gamma k plus 1, let's say, or gamma k, yeah, gamma k, if I take k equal to 1, I should get mod I divided by 4. So this is bigger than or equal to mod I divided by 4 power k. Okay, so tell me if you agree to this or not, whatever I have written. Yeah, and if I need to repeat this argument again. Yes, Abhishek, I can't hear properly. It's fine. Okay, so therefore, you see, the process is like when you consider the rectangle R1, so then again you subdivide into four equal parts, and then let's say there will be one rectangle, let's say this time this one, where the integral would be at least 1/4 times the integral over gamma 1. Okay, so therefore, if you put both these two together, then you will get that over this rectangle, this particular inner rectangle, the integral will be bigger than or equal to mod I divided by 4 square. Okay, so if you continue doing like this, you are going to get this nested sequence of rectangles or triangles, and with these properties. Okay, so now here, so I'm sure you guys have studied Cantor intersection theorem. Yes, have you studied Cantor intersection theorem or not?
Yes, sir.
Yeah, so what do I get when I have this nested sequence of rectangles or triangles like this? Sorry.
A single point.
Yeah, so we are going to, if we take the intersection, then the intersection is going to be non-empty and is going to have one unique point. Okay, so anyway, here the unicity is not going to be very useful, but let's say nevertheless we are going to get one point in the intersection. So by Cantor intersection, so here you see all these rectangles; these are compact sets, right? So by Cantor intersection theorem, we get intersection of these I's I bigger than or equal to 1 is non-empty. Okay, of course, it's going to be singleton because the diameter of the Ri's are going to 0 as well, because each time it's getting decreased by a factor of half. So anyway, so this is non-empty. So let that I have a point z naught which belongs to this intersection I bigger than or equal to 1 Ri. Fine. So now I have this, and the moment I have got a point now, so this point, remember from the picture like I was drawing. So initially I had this picture, right? So I was drawing this diagram, and I said that my next rectangle could be this one. Okay, so in fact, from here you can see that the point z naught that I'm going to take, or that I'm going to get eventually, need not lie on the boundary of the rectangle, but it can also lie in the interior. Okay, so whatever might be the case, I have this z naught inside here, and you see this z naught belongs to the ball, right? So here I had started with a ball, so it belongs to this ball bar, and therefore what I can say is that my function f is holomorphic and z naught. So we have f is like, let's not write so. So we have we have f is holomorphic at z naught. Okay, so what does that mean? It means that limit h tends to 0 or let me write it in terms of z tends to z naught, f of z minus f of z naught divided by z minus z naught is equal to like this exists. Okay, and which is f prime of z naught. So this is what we have, right? So this particular ratio goes to f prime at z naught as z tends to z naught. Okay. So if you have this, then you will be able to write. So this means what? That is means in another way I can write limit z tends to z naught. This f of z minus f of z naught divided by z minus z naught. So here I can subtract z minus z naught times f prime of z naught is equal to 0. Okay, so I get this one. So this implies we have a function. So that is, I can write f of z as f of z naught plus z minus z naught times f prime at z naught plus z minus z naught times some function of z, let's say h of z, where h of z goes to 0 as z tends to z naught. Okay, so you agree to this? Yeah, fine. Yes or no? Agree to that?
Yes, sir.
Okay.
Yes, sir.
So I have this. Now what I'm going to do, I'm going to let us observe what is this function h. So h of z, if I let us take z not equal to z naught, then I see that h of z is nothing but f of z minus f of z naught divided by z minus z naught minus f prime of z naught. Okay, if z not equal to z naught. Okay, so now will you say that this function is a continuous function, for instance, if z not equal to z naught? Yeah, because f is a continuous function and the denominator does not vanish if z is not equal to z naught. So therefore, for this particular thing, we know that h is a continuous function. And now we know that as z tends to z naught, h of z goes to 0. So if I put 0 for z equal to z naught, then uh, is continuous on VA, whatever, what was R? It was R or delta? Yeah, VAR. Fine. Do you agree to this? Yeah, then this is a continuous function. Tell me yes, no, something. Yes?
Yes, sir.
Yeah, so this is a continuous function. Fine. So why I was mainly interested in making this continuous is that I wanted to, I will be integrating this one. Okay. So anyway, Uh, so this is my expression of my f. F can be written in this way. So in this ball, and this is going to be continuous. So fine, I have this, and now therefore you see I get an expression of f. So I'm going to use that. So what do I get? So integral of f over gamma I. Let's say this is therefore becoming integral over gamma I of the function f of z naught minus or sorry f of z naught plus f prime of z naught f prime of z naught times z minus z naught plus h of z into z minus z naught. Okay, so I need to integrate this function to get the integral for f. Okay, fine. Now here notice two things. So first of all, this guy is a constant. Okay, now if I
Yes.
integrate a constant over a closed curve, what am I supposed to get?
Zero.
Why?
Because sir, it is static and end point and starting point is same.
Yes. So why the integral should be zero? Sorry.
Primitive exists.
Exactly.
Primitive.
So
It
we
is independent of path.
absolutely. So we have a primitive over here. So I can take, let's say, the function this times z, and if I take its derivative, I'm going to get the constant. So I have a constant, so it has a primitive, so that integral is zero. Okay. Now again, f prime of z naught is zero, and
Constant.
this part, sorry, f prime of z naught is constant, and this part z minus z naught, this is a polynomial function in z, right? So can I say something about the integral over gamma I for this particular factor? Can I say something?
Again zero.
Again zero. Why?
As primitive.
Yeah, again I am going to have a primitive, so that is also zero. So since these two things have, so both of them have primitives, yes, I have primitives. So what I get, so this implies integral of f over gamma I is nothing but integral over gamma I of hz times z minus z naught. Very nice. Okay, that's good. Now what I'm more interested in is I would like to now, so you see I have to prove that the integral of f over gamma I, in some way I need to make it very small, and so that I can say that the actual integral I is equal to 0. So what I am going to do is I am going to estimate this part. Okay, so I do not know a priori what is this integral. I do not know whether it's 0 or not. So what I have to do, I have to estimate this integral, and then I would like to get whatever is desired. Fine. Now if I want to estimate this integral, then you have only one thing in your hand. So that is like you can, for example, try to use ML inequality. Okay, so this is what you can do. Fine. So now let us try to see if we means how we are going to use the ML inequality. So for instance, what I can do is that note, if I take, so we know how the length of gamma and the diameter and all of that means how do they change. So therefore what I can say is that we know, so note we have that length of gamma k is equal to 1 by 2 power k length of gamma. So that's first thing that we notice. And similarly, diameter of gamma k is 1 upon 2 power k. Diameter of, sorry, yeah, diameter of r k is 1 upon 2 power k diameter of r1. Or yeah, okay, so this is what I have. Fine. I get this one now. Let's see, just a moment. So yeah, that is fine, I guess. Okay, okay, so that's all right. Yeah. So just a second. So here it should not be gamma 1, it should be rather gamma, right? Let me just check once. Yeah, so at each stage I am getting reduced by half. So if I continuing doing this, I am going to get half power k. Yeah, so that should be gamma and r. So this one is r. Sorry. Yeah, so diameter of r power k is half 1 over 2 power k diameter of r. Yeah, because if I put r equal k equal to 1, I should get diameter of r1 is half of diameter of r. Anyway, so this is what I get. Fine. Once I do that, so let's consider this thing. So now we, if we take, so here I, as I said, I need to estimate this integral. So of course I know now what is the length of the integral, that I know. So I have to now estimate the integrand. Okay, so how do I estimate that? So first of all, observe. So now note, if so my z is in gamma I, and so therefore this is in, for instance, in Ri, and z naught is in the intersection. So therefore then, if I consider the distance between n z and z naught, so this is less than or equal to diameter of Ri. Okay, and diameter of Ri is equal to 1 upon 2 power I diameter of R. So this is 2 power I. Do you agree to this? Yeah? Tell me if you agree to this or not. Yes? No? Something? Yeah, fine. So therefore, distance between these two quantities, z and z naught, so that distance in absolute value is less than or equal to 1 upon 2 power I diameter of R. Fine, all good. So now, again, so many nows I'm writing. Since, so what's the property of H? Since H of Z tends to 0, as Z tends to Z naught, for any given epsilon positive, there exists a delta positive such that uh, on B delta Z, sorry, B Z naught comma delta, mod of H of Z is less than epsilon. Can I write this one?
Yes, sir.
Okay, so uh, now you see I have that's the case, and therefore I have got delta. So whenever distance between z naught and z is so such that, so let me write not on, such that z belongs to this implies mod of h of z is less than epsilon. Okay, so I can choose a delta positive which works in this way. Fine, that's good. But now I need to consider this integrand. So here I have got a bound for h of z, but that's valid on this ball b z naught delta. So let us do something more. So now uh, we can choose, tell me if you agree to this or not, choose k such that, or k in n, such that this 1 upon 2 power k diameter of R is less than delta. Do you agree that I can do this? Yeah.
Yes, sir.
So because this part is going to 0, isn't it? So delta is some positive quantity, so I can do this. So once I do that, so this implies on gamma on RK. So this is which, so this is nothing but diameter of RK. Remember. So on RK we have mod of z minus z naught is less than delta. So this implies on RK we have mod of f of z, sorry, not f of z, mod of h of z less than epsilon. Okay, so hence what do I get? Hence, if I consider the integral on gamma k of our function h of z, or let us take f of z for the moment. So the function f, so this is less than or equal to, or this is rather equal to, in absolute value integral over gamma k h of z into z minus z naught. So this by ml inequality, let us try to understand what is the max means for what is an upper bound for the integrand. H is bounded above by epsilon, z minus z naught is bounded above by the diameter, so that's 1 upon 2 power k diameter of r, and the length of the integral is bounded above by 1 upon 2 power k length of gamma. Agreed? Do
Yes,
you
yes.
agree to this estimate? Fine. Okay, now what I have, I know that this quantity in absolute value is bigger than or equal to, so this quantity is bigger than or equal to mod I divided by 4 power k, correct? So if I put all this together, what am I get? What am I getting? So since in absolute value integral of gamma k over f is at least mod I divided by 4 power k, we have mod I is less than or equal to epsilon times, you see the 2 power k and this 4 power k can be cancelled, therefore
Risk imposed.
Yes, sir.
okay, sorry, my internet dropped. So yeah, for me the internet, the power went off. Okay, so now do you see my screen?
Yes, sir.
Hello. Yeah. So mod of I is less than epsilon times diameter of R times length of gamma. Length of gamma. Okay, so this is true for all epsilon. This is true for all epsilon positive. This implies mod of I equal to 0, which implies I equal to 0. So do you agree to the argument that I have given? Yeah.
So,
So therefore, what I see is that I can show that okay, not only so here of course what I get is that the integral over of the function az times z minus z naught, that is 0, like, or that can be made arbitrarily small, and therefore the integral over f is can also be made arbitrarily small. Okay, so this is the proof, and it tells us that now if I take any holomorphic function that's going to like if I take an integral over a closed rectangle or a triangle, it's going to give me 0. Okay, is this clear to everybody? Yeah. So in fact, here I have taken you have seen that I have taken my function to be holomorphic on a disk. Okay, but in fact, this shows that you can in fact take any open set where you don't have any holes. Okay, in the sense I was telling you at the time of applying Cantor intersection, we were taking this intersection of these integrals and all, sorry, these rectangles and all that. So therefore, it was important that when I apply Cantor intersection, the point that we get, that needs to be like in our that needs to be a point where our function is holomorphic. Okay, so therefore, all these things are going to, like, whatever this rectangle theorem that I have proved, actually rectangle or the triangle theorem that I have proved, with the domain being just a ball, simple ball, the proof goes through as it is, as long as you take any rectangle, and then that rectangle should be completely inside the ball, in the sense that not only the boundary but the interior of the rectangle. If as long as that is inside your set, you are through. Okay, so that means you should not have any kind of holes in your set. So you should not have any kind, like for example, if I take punctured plane, let's say complex numbers minus 0, so those kind of sets are not going to work for us. Okay, so I can replace this open ball by any kind of set where we are not going to have holes. Okay, so that's the primary thing. At this moment you can keep it in mind. Okay, because what you saw is that we were applying this Cantor intersection theorem. So therefore it was really important that we get that means by taking Cantor intersection, the point that we are supposed to get, that should really be inside, like my function f should really be holomorphic or differentiable at that point. Okay, so this is what is the key thing over here. Fine. Okay, so is that clear to all of you? Yeah. Yes.
Yes, sir.
Okay. So now what I am going to do, I am going to show first of all. So I was talking about all this, primitive and all that, right? So we have seen if a function has a primitive and all this, then we can have that the integral is equal to 0. And here we have seen that if I start with a holomorphic function in a ball, then that function, for that function, the integral is becoming 0. So what I'm going to now prove is that using this, we are going to actually show that any holomorphic function, let's say defined on a ball for simplicity, we will always have a primitive. Okay, so that's the theorem next that I'm going to prove. Theorem. So let f be a holomorphic function on a ball. Let's say I'm going to work like this. On a ball, let's say bar, then there exists a holomorphic function capital F on bar such that capital F prime is little f on this ball. Okay, so if I have a holomorphic function on a ball, then I will be able to find out a primitive for that holomorphic function. Okay, so this is what we need to do. And now here I need to tell you what means. I need to remind you one thing, that how one can. So I need to find a primitive, right? That's the business. So how find a primitive? So of course I had written one part of the fundamental theorem of calculus somewhere here. Let me see. Where was it? Okay, yeah, here the real version was that suppose there exist things like this, then this integral is going to become fb minus fa. Okay, so that was the fundamental theorem of calculus that I had stated. Okay, but here what is important is that I tell you the more general statement that like one sees in R. So in R, how do you like really, if I have to state the fundamental theorem of calculus for continuous functions, it goes something like this. Okay, so recall this is fundamental theorem of calculus for like continuous functions on R. Okay, on R or on subsets of R. Subsets of R. Okay, so what is that? So let f from closed interval AB. So let us take, I am going to work with these kind of subsets. Okay, so let f from closed interval AB to R be a continuous function. Okay, so suppose, yeah, I see there is some lag. Stable. Okay, let me try to connect to that. Okay, so suppose I have this is the this is a continuous function. Don't suppose anything. Okay, so define. I'm going to define. This is still lagging. What is going on? Okay, so define capital F of x. Yeah, this should be fine now. Okay, so define capital F of x in the following way. Define F or capital F from closed interval a b to r such that capital F of x is integral from a to x ft dt. So I'm defining my capital F in this way. Then what one can prove is that then there are really important properties of this capital F function. This capital F is uniformly continuous on closed interval AB. It's continuous, therefore uniformly continuous. And this is also capital F is also differentiable on open interval AB. And I have capital F prime is equal to little f on open interval AB. Okay, so hence integral of a to b little ft dt is capital Fb minus capital Fa. So this is the version of fundamental theorem of calculus that I want you to keep it in mind. Okay, so in that case, how did I find, like how did we get hold of this primitive? We got hold of this primitive by taking integrals, right? So let us take means let us decide a starting point, let's say a, and then I said that if I take integral from a2 up to x ft dt, that's going to give me a function of x, and this function was differentiable and the derivative was giving me this function little f. Okay, so therefore we are going to do a similar thing over here. Okay, we are going to define our primitive in a similar fashion. Okay, I'm going to fix one point. So here, of course, I have this ball BAR, so I can fix the center, for instance, here. And then I am going to define a function where I can, like, by taking integrals on the line, like it means by taking a path from A to that particular point and integrating along that path. Okay, so now the point is, of course, there could be several choices of path joining, like joining two points. So the way we are going to define this path, that's not a universal definition. Okay, so but what I'm going to do is that we are in some way, the way I'm going to define a path that should means like we will see that should be means we should have a setup in such a way that we are able to apply our triangle theorem or rectangle theorem. Okay, so this is what I am going to do. So like I said, exactly like in the fundamental theorem of calculus, in the real variable, in the real version, the definition of this primitive comes from taking integral of our function from a to up to x. So that means essentially you are integrating your function on the interval a to x. Okay, so therefore that is essentially line joining a and x. So here also we would like to do something similar. Okay, and as I said, you could join two points in various ways. Okay, but we don't we will take one particular definition and one particular path so that we can use this rectangle theorem or triangle theorem. Okay, so depending on which one you want to use, you will have to kind of decide which path you want to take. Okay, so That's all. So this is something I want you to keep it in mind. So here for simplicity I'm going to use triangle theorem. So therefore I am going to define the path in that way. And since you see I am working with for instance an open ball, so essentially this is like some kind of convex set and all this. So therefore if I take 2 points from my open set, if I join these 2 points by straight line, the line segment is going to be inside my domain, so I will not run into any kind of trouble. Okay, so let's see what am I going to do. So define, so let z1 and z2 belongs to bar. Okay, so we can define um, path joining z1 z2. We can define a path, let's say gamma z1 z2, gamma z1 z2, joining these 2 points by uh, sorry, this is z2, by simply taking the line segment joining z1 and z2. Okay, so if I have 2 points z1 here, z2 here, then what I am going to do, I am just going to take the line joining these 2 points z1 and z2. That's my path gamma z1 and z2. Okay, so of course here I have a direction which is inbuilt. So this is in this direction, gamma z1 z2 is starting from z1 going up to z2. And if you take start from z2 and then come to z1, it will be in the other direction. Okay, so essentially gamma z1 z2 is the, or gamma z2 z1 is the reverse path of gamma z1 z2. Okay, so anyway we have this one. So means, so actually I should have given a name. So this theorem is called the integral theorem. Yeah, so this let me call it somewhere here. It's called integral theorem. Okay, so I need to prove this integral theorem. So I'm going to use the triangle theorem, means like the version that I proved over here. So I'm going to use triangles. Okay, so if you want to use rectangles, you have to define different kind of paths. Okay, so anyway, so here the most natural thing is to join two lines, straight lines like this. So I am doing it like this way. Okay, so here exactly now that I have a path, like we know, we understand what is a path. So following this, what I am going to define, so define capital F of z is integral of f over the path a to z. So a is my center at of this ball bar. Now for all z in bar, I am defining capital f as integral of little f along the path gamma az. Okay, so do you see this one? Do you see this? Yes, that this definition is therefore quite analogous to the one which we had in the real case, right?
Yes.
Yeah, so like, so therefore it means, you see, since we are studying something little bit beyond real analysis, so you also need to keep it in mind what happens in R and how things happen. So we kind of take some intuition from there and create this function capital F. Fine, now I need to show this capital F prime is little f. Okay, so if I need to show that capital F prime is little f, then it's natural to consider, so natural to consider capital F of z plus h minus capital F of z, because this difference when I divide by h should go to little f of z, right? So therefore it's natural to consider this difference. Now my claim for this particular quantity is that so this is our claim, that f of z plus h minus f of z capital is nothing but integral of f gamma from z to z plus h. Okay, so we need to see this. How do I see that? Okay, so for this let's try to draw a picture. So let us have 3 points A, let's say z over here, and z plus h somewhere here. Okay, so that's a to z, this is z to a, and this is z to this. Okay, so by triangle theorem you will agree that this integral is going to be equal to 0. So note, by triangle theorem what do I have? We have integral of f over gamma az plus integral of f over gamma z to z plus h plus integral over f gamma z plus h to a. This quantity is 0. Okay, so therefore what I get is that integral for gamma over z to z plus h over f is nothing but minus integral gamma z plus h to a to of f minus integral of f over gamma z to, sorry, yeah, a comma z. Okay, so here you see the first one, the first term I will be able to write as I said, like gamma z1 to z2 is the path starting from z1 ending at z2. So gamma z2 to z1 is exactly the reverse path, this time starting at z2 and coming to z1. So therefore here what I have, this I can write gamma of a to z plus h minus f gamma a to z. Tell me if you agree to this or not, whatever I have done so far. Yeah, so once I have this, you can immediately note that this is nothing but, by our own definition, this is f of z plus h minus f of z. All of you agree to this? Yeah.
Yes.
Yes,
Sure.
sir.
So therefore, this claim that I have made, that is vindicated. Great. So let us do the following. Now, what do I have to do? I have to show that limit z tends to 0. So next we show limit h tends to 0, f of z plus h minus capital F of z divided by h is equal to alpha, where alpha is my f of z. If I can show this, then will I get that capital F prime is little f? Tell me. Yeah.
Yes, sir.
So let us consider the difference now. Okay, so let's consider the difference. Note, so I am going to consider this difference f of z plus h minus f of z. Why I wrote alpha is that so that you do not treat z as the variable. Okay, here. Okay, so it's just a constant because I am going to get a value, precise value. So this one is alpha, and I write this as 1 upon h integral over z from z gamma of z to z plus h f minus, I can write this is as integral over 1 over h alpha gamma of z to z plus h. Okay, so here the length of the path is just h, that's clear. So the constant function alpha, I can just write that this is integral over like gamma from z to z plus h 1 upon h. So alpha is just constant. So this is what I can do. Okay, so you can write down immediately. This is like there is nothing surprising in this. So once I have this, this will be equal to 1 upon h integral gamma z to z plus h f minus alpha. I can write like this. Okay, so all of you agree to this? Yeah, tell me if you could you follow this or not?
Yes.
Okay, great. So I have this particular integral. Now I need to show, as I said, so this is the limit that we want to get. So therefore, I need to show that this quantity goes to 0 as h tends to 0. So therefore, again, what do we have? We have only the ML inequality at our surface. So I need to somehow estimate my function. Okay, so what would be my function? That is what I need to see. Fine, all good. So now here, notice one thing. I have my function little f, which is given to be holomorphic, right? So in particular, my function little f is continuous. Note f is holomorphic, and that implies f is continuous. Okay, so once f is continuous, what I get? So for any given epsilon positive, there exists delta positive such that whenever such that um, for all, let's say this time I write a different variable s, for all s minus z less than delta, we have mod of f of s minus f of z, which I write it as alpha, is less than epsilon. Okay, so whenever the distance between s and z is less than delta, so we have fs and alpha, distance between fs and fz is less than epsilon. So continuous. So this is what I get. Okay, so that's from continuity. Fine. So once I get this particular thing from continuity, then what do you see? This is true in a delta ball around, so this I have written different ball, right? Yeah, that's fine. So this is what is happening in a delta ball around z. Okay, so this estimate is valid in a delta ball around z. So what I am going to take, I am going to take h in such a way so that z plus h is in this ball. Okay, so now, so for h such that z plus h is in b a delta, sorry, b z delta, because anyway your h should tend to 0, so z plus h should tend to z. So eventually z plus h needs to be in any neighborhood around z. So you take h, so that z plus h is in this. Then what I can say, so we have so in this path between gamma z to z plus which we have on gamma z to z plus h, on this path, this difference of this function is less than epsilon. So we have mod of f of s minus alpha is less than epsilon. Okay, so on that path itself, the absolute value is uniformly bounded by epsilon. And what is the length of the path? The length of the path, as I said, it's clear that the length of the path is mod of h. Okay, so this I am not going to calculate. You can check if you wish. Note that length of uh, gamma z to z plus h is going to be nothing but mod h. Okay, so we have, if I consider this distance in absolute value, when I am trying to take apply ML inequality, what I am going to get? F of z plus h minus f of z divided by h minus alpha is less than or equal to, you see, this is this integral, and I have, if I want to apply ML inequality, then what do I get? M is nothing but epsilon over here. I can take M to be epsilon over here, and length of the path is mod of h. So in absolute value, this is h mod h into epsilon into mod h. So that gets cancelled. So this is equal to epsilon. Now this is true for any epsilon positive, right? Hence we get no, sorry. So this is of course true for any epsilon positive, but your h is tending to 0. So let me just not write this. So I have shown that whenever you take your h in such a way that z plus h is in this ball bz delta, you are getting that this quantity is less than or equal to epsilon. Okay, so we have z plus h, or yeah, z plus h belonging to vz delta, implying mod of f of z plus h minus f of z divided by h minus alpha is less than epsilon. So this implies limit h tends to 0, f of z plus h minus f of z divided by h is equal to alpha, which is little f of z. Okay, so hence we get capital F prime of z is f of z. Okay, and of course my z was an arbitrary point of our open ball bar. So we kind of got that this function little f, any holomorphic function for that matter in a ball, is going to have a primitive. Okay, so there will always be a primitive and of a holomorphic function on a ball. Okay, so here one thing that you need to remember is that we used holomorphicity of little f in two places, like the first one being we applied this triangle theorem for f, little f. So we used triangle theorem, and we had seen for triangle theorem we needed holomorphicity, and another place where we used the continuity of f. So there we have. Okay, so effectively you see I needed continuity, and at another place I needed this triangle theorem. Okay, so in fact what we can say is that, so remark, the statement of integral theorem. So I said, what is the integral theorem? The integral theorem is this existence of primitive, that guy. So the statement of integral theorem holds for any continuous function for which, let's say, triangle or even rectangle theorem, any of this is fine, holds. Okay, so all I need then here in this proof is that I should be able to apply my triangle theorem or the rectangle theorem, and we needed continuity. So therefore, if I have this, if I have a continuous function for which this triangle theorem is valid, or let's say rectangle theorem is valid, then we will be able to show that means we will be able to find a primitive. Okay, so is this clear to all of you? Yeah.
Yes, sir.
Okay, so this is one thing, one point which I would like to highlight. Of course, the integral theorem as is important, but you need to also understand that the integral theorem holds true whenever you have the triangle theorem together with continuity. So if my function satisfies triangle theorem, no matter what triangle you take and all that, and if let's say by some reason, like by some hypothesis, you could show that a function is satisfying the triangle theorem or rectangle theorem, we will see some examples. And if you can say that the function is continuous, then you will see that the conclusion of integral theorem will hold true. So that means if a function which is continuous and satisfies triangle theorem or rectangle theorem, then it's going to have a primitive. Okay, so that is what is the key thing. Okay, so here I have two quick corollaries. Okay, so the first corollary being is that let f be a holomorphic function on a ball. Okay, so here on a ball bar. So suppose I have a holomorphic function with a function which is holomorphic on a ball, then for any smooth closed curve or smooth or piecewise smooth closed curve, gamma, we have integral of f over gamma is 0. Okay, so can you tell me how can I prove this? I have a holomorphic function on a ball, and then if I take any closed curve, this means like piecewise smooth closed curve, then I am going to get the integral to be equal to 0. How do I get this? Think about it and tell me how can I prove this? Sorry?
F has primitive from previous theorem.
Yeah, very good. So f has primitive from previous theorem, and what did we see? We saw that whenever
Initial and ending point are same.
absolutely. So whenever we have a primitive, then this I think it was done not in the last class, right? But the class before. Let me see. Was it in the last class? Probably. Yeah, here. Yes, in the last class only. So we had seen that if f has a primitive and gamma is closed, then the integral is going to be 0. Okay, so here what I see is that if I take any holomorphic function, then it's going to have a primitive, and therefore on any closed curve the integral is going to be 0. Okay, so this is something which special, that property that we see for holomorphic function. So what in turn we have proved? So initially we had proved that for triangles or over rectangles, the integral of a holomorphic function is 0. But now I have proved that if you take any piecewise smooth closed curve, then also the integral becomes 0. Okay, because using that triangle and rectangle theorem, I came to this existence of primitive, and using that I have proved this closed curve theorem. So the picture that I want you to keep it in mind is that suppose I have this rectangle and triangle theorem. Suppose this is true, then this will imply, so provided your function is continuous, then you will have integral theorem. And the moment you have integral theorem over closed curve, the integration is going to become 0. So like you will get integral of f over gamma is equal to 0. Okay, so this one, let me write down the name. So this corollary is called closed curve theorem. Okay, and I think I had given the name of this section as closed curve theorem for holomorphic function. So this one is called closed curve theorem. So what I see eventually is that this integral theorem implies closed curve theorem. Okay, so any function which satisfies rectangle theorem with continuity and have like that implies closed integral theorem, and therefore I get closed curve theorem. So if I have just a continuous function which satisfies rectangle or triangle theorem, for those functions also the integral along any smooth piecewise smooth closed curve is going to be equal to 0. So is this clear to all of you? Yeah. Okay, fine.
Yes, sir.
Okay, so you see, all this when I said, or like when we started doing all of that, our aim was to prove, you know, to show that a function which is holomorphic is going to have a power series expansion. Okay, so if it means if I need to get to that, I will have to work with one function. Okay, so that function a priori I will not know that it's holomorphic, but what I will know about that function is that that function is going to satisfy this rectangle theorem or triangle theorem, and it's going to be continuous. Okay, so that's why it was really important to uh, understand that closed curve theorem holds true for any continuous function for which rectangle or triangle theorem holds true. Okay, or the integral theorem holds true for any function for which this rectangle or triangle theorem holds true, any continuous function. Okay, fine. So here I am going to, as I said, I have a holomorphic function. The primary aim is to show that this has a power series expansion around any point that you wish to take. So we need to work with a particular kind of a function. Okay, so let's do that. So as I said, this is means we are proceeding towards writing down power series expansion of holomorphic functions. Okay, so there are several steps. So now that we have understood this rectangle theorem, integral theorem, and closed curve theorem, we are going to uh, take one step further, and we are going to prove that this rectangle or triangle theorem, of course we now understand this holds for holomorphic function, but we are going to prove this or exist this we are going to show that the rectangle theorem and the triangle or the triangle theorem holds true for another function which is very closely related to a holomorphic function, and that's going to aid us in proving the power series expansion. Okay, so let's see what do I mean by all this. Okay, so here, okay, what do I have? Fine. So let f be a holomorphic function on some ball bar. Okay, then for alpha, what is going on? So then for alpha belonging to bar, so if I take alpha from bar, define define g of z, which is f of z minus f of alpha divided by z minus alpha for z not equal to alpha, and f prime at alpha for z equal to alpha. Okay, so I'm going to work with this particular function f of z minus f of alpha divided by z minus alpha. I mean, this is essentially the kind of the derivative that we are going to take that we are going to get for f. So at the point alpha it's f prime of alpha, and otherwise it's fz minus f alpha divided by z minus alpha. Okay, so in fact from the definition of g it is clear that this function g is continuous at alpha. Do you agree to this?
Yes, sir.
Yeah. Okay, so it's clear that g is continuous at alpha. And will you also agree to the statement that g is holomorphic on bar except possibly at alpha? Will you agree to that as well? That this function g is holomorphic on bar except possibly at alpha and is continuous at alpha. Okay, so what is g? So g is holomorphic on bar except possibly at alpha, because at alpha I do not know what happens, and yet but g is continuous at alpha, that I can definitely ensure, because at alpha the value is whatever is the limit of g at, as z tends to alpha. Agreed? Okay. So you see the eventually what I would like to show at the end, that I have written that this is holomorphic on bar except possibly at alpha. So I'm going to remove that. Eventually I'm going to show that G will be actually holomorphic at alpha as well. Okay, so this is important for our context. You will see why. So we will prove that G is holomorphic. In fact, G is in fact holomorphic at alpha. So this we are going to prove, but you will see why this is important. Okay, so to do that, what I am going to show, see at this moment, of course, from the information that I only have that G is continuous in the whole ball, and let's say it's also holomorphic on BAR except possibly at alpha. So in general, I have continuity. That just keep that in mind. Okay, so the first thing that I want to prove here, theorem. So that what I want to prove is that rectangle slash triangle, whichever you want to take, theorem holds for G. So first of all, I want to prove this, that the rectangle theorem or the triangle theorem is going to hold for the function G. Okay, so therefore what I am going to do, I am going to take a triangle and or a rectangle, and I'm going to show that if you integrate G on that rectangle or triangle, you are going to get 0. Okay, so this is what my claim. Okay, fine. So here I'm going to do the following. So let's quickly prove this. Let me just see if I have anything like that. Yeah, so I'm going to, yeah, the proof is not very complicated. So what am I supposed to do? So let R be a, so I'm going to show it for triangle. You can do it for rectangle also. Let R be a triangle, and let's say here, of course, I was defining on BAR, right? So let R be a triangle on BAR. We show integral over gamma of G is equal to 0, where gamma is the boundary. Okay. Okay. So how do I do that? Let me tell you the following. So suppose, so this alpha is a problematic point, which we understand, right? Because except for alpha, G is holomorphic everywhere. Okay. So suppose this alpha does not belongs to the rectangle. So that means, it means when I say that, when I think of a rectangle or triangle, I am not only looking at the sides but also the interior. Okay, so when I'm saying that alpha does not belongs to R, that means alpha neither belongs to R nor belongs, neither belongs to the sides nor in the interior. Okay, so this is what is the scenario that I take. So suppose alpha does not belongs to R. So if alpha does not belongs to R, then what I can say, G is actually holomorphic on a neighborhood. Okay, so you have this rectangle, so on a neighborhood of R, G is holomorphic. Okay, so can I say this? Tell me if you agree to that. Yeah, so I have, so the picture should be something like this, that I have a rectangle like this, and so let's say this is my R and my alpha is somewhere away. Okay, so I will be able to have some small open neighborhood around R, need not be a ball, but some open neighborhood around R where my function G is going to be holomorphic. Okay, because R is a compact set, I can do this. Yeah, yeah. Okay, so is it clear? Yeah. So now that G is holomorphic in a neighborhood of R, what I can say, we get, so you see, I only told you that while doing this rectangle theorem and triangle theorem, all is important is that interior in the function should be holomorphic in an open set containing the entire rectangle or triangle, whatever you are working with. So we get integral of G along gamma is 0. Do you agree to this? Yeah? Yes or
Yes.
not? Tell me.
Yes,
So
sir.
this is my triangle theorem for holomorphic function. Because already in this open set, so let us call it U, in this open set, my function is holomorphic. So by triangle theorem for holomorphic function. So this case is done. Yeah. Good. So that's the first case. Let's do the second case. So the second case being let alpha belongs to gamma. So gamma is the boundary. So let us have a scenario where my alpha is in the interval like is on the triangle gamma. Okay, so let me draw the picture again. So let's say I need to draw a bigger picture here because I want to make a lot of subdivisions. So let us say alpha is somewhere here. Okay, so let's say this is my alpha. So what I am going to do over here, I am going to break my triangle into several pieces. Okay, so how am I going to do? So you just and I am going to take smaller and smaller integrals. Okay, so here let's say I take a point over here somewhere inside the triangle, and I break my actual triangle into a lot of pieces. Okay, like that. So effectively 5 triangles I have. Okay, so the main triangle is broken into 5 triangles, and of course the alpha is now inside or on the boundary of one of the triangles. Okay, so the actual bigger triangle, the boundary is gamma. So let's say that for this one it's gamma 1, it's one, this one is gamma 2, this one is gamma 3, this one is gamma 4, this one is gamma 5, let us see. And the kind of things that we have done already before will tell you that the integral over gamma is same as sum of the integrals over gamma i's. This you can see it immediately because the means the internal integrals are going to get cancelled. Okay, so exactly what we have done before, the same thing can be done over here. So in this case we break the integral into 5 subintegrals. Okay, 5 subintegrals with the property that, so here I wrote this one as gamma. Okay, so let it be as 5 subintegrals with length of gamma 4 to be arbitrarily small. So gamma 4 is the one where alpha lies. Okay, to be arbitrarily small. So that is how I am going to break my triangle in this way. Okay, so note the integral of g along gamma is summation I from 1 to up to 5 integral of g along gamma I. Okay, so this is what I have. Fine, all of you agree to this? Do you agree to this or not? Whatever I have done, I can break my triangle into 5 sub-triangles, and with my main focus will be that the triangle containing like where the alpha lies, that triangle I am going to make very very small. Okay, so here I have drawn a small picture. Of course, you can draw a smaller picture and things like that. So I am breaking into 5 sub integrals. Okay, now here you see for all the triangles gamma 1, gamma 2, gamma 3, gamma 5, in all of them the alpha is staying away. Okay. So in the case when alpha does not stay like lies either inside or in the boundary, then what I can say is that by case 1 we have integral over g of gamma is integral over g of gamma 4. Tell me if you agree to this or not. Yeah, do you agree to this or not? Come on, I get no response at all. If you do not agree, please tell me that you don't agree. That is also fine. I am going to repeat that. There is no problem. Please tell me, means if you are not understanding something or anything like that.
Yes, sir.
Yeah. So here, except the integral gamma 4, all other integrals are going to vanish because you see my alpha is strictly staying away from my triangle. Okay. So by case 1, I'm going to get that the integral is going to be like the whole integral is only going to be integral over gamma 4. Now you see, as I said, of course I have the chance to take or option of taking gamma 4. The triangle that I have drawn, I can of course draw a smaller triangle. Nobody is going to object to that, right? I can make my gamma 4 as small as I wish. So note that, again note, gamma 4 can be made arbitrarily arbitrarily small. So what does it mean? So that is, given any epsilon positive, we can choose gamma 4 such that length of what is going on such that length of gamma 4 is less than epsilon. So suppose I have this, and now g is a function which is a continuous function. So I am going to integrate g, which is a continuous function. So this will be clearly is going to have a bound in a neighborhood of alpha, like because this is anyway holomorphic in this open AR. So for example, I can even choose a compact subset of ball AR containing alpha. Okay, so therefore now we can find m positive. So this m is independent such that mod of gz is less than or equal to m for all z. Let's say in the r is a compact set. So I can find an uniform bound. So that implies integral of g over gamma 4 is in absolute value less than or equal to m times epsilon. Okay. And this is true for any epsilon. Okay, so of course I can take smaller and smaller side like length for this gamma 4, and this is true for any epsilon positive. So this implies integral over gamma 4 of g is equal to 0, and that will imply integral of g over gamma is equal to 0. All of you agree to this?
Yes, sir.
Yeah. Okay, so the last case is rather simple. So let me just quickly complete that. And just, yeah, I just have a few minutes. So case 3, what is case 3? So here you saw that we had alpha was not in R. The first one was alpha was not in R, means neither in the boundary nor in the interior. Next one was alpha was on the boundary, so that means alpha was in the bound on gamma. And the case 3 is alpha belongs to the interior. Okay, so alpha is inside R. Okay, so the case 3 is going to be very easy. Okay, so alpha is inside R. So therefore, again, let's draw the picture. So I have a triangle. This is R, and I have alpha somewhere here. Okay, so let me write it in a prominent place. Alpha is like this. So what I am going to do in this case, I am just going to break my triangle into two pieces. I'm just going to connect these two lines, and I'm going to So I'm going to draw two sub triangles this time, like this. So here, of course, we understand the integral over R is like over the boundary of the actual triangle is same as integral over the sum of the triangles of sum of the boundary of these two sub triangles. Okay, and here this time what happens? The alpha lies on the boundary of these sub triangles. Okay, and by case 2 we have already seen that if alpha lies on the boundary, then the integral is going to be equal to 0. Okay, so in this case alpha line means in this case we break this in this case we break R into two sub two sub triangles, each of which contains alpha on the boundary. Okay, then by case 2, we get integral of f of g over gamma is equal to 0. Okay, because I can then just break it into two pieces and I will get it. So is it clear to all of you? Yeah. Yes. So no, tell me.
Yes, sir.
If you, yes, you have you understood this? Yeah. So what we see that this triangle and this rectangle theorem that holds for G, and if you have followed this array of implications, then what you will get immediately as a corollary, integral theorem. G is already continuous, so integral theorem holds for G, and as a corollary you get closed curve theorem holds for G. Okay, so these are the two statements that we finally get, and in the next class I'm going to prove Cauchy integral formula, which will give us this power series reference. Okay. So we are already time, so let us stop here and stop the recording, and you can tell me if you have any questions.